In this lecture, we're going to revisit some ideas about conditional statements that we talked about in the propositional logic lectures and apply them to universal conditional statements. Now, there really isn't much that's new or interesting here. The ideas are going to be the same, but with for every x tacked onto the front. So we're going to move through them pretty quickly. So we can form the converse, inverse, and contrapositive of a universal conditional statement by following the same rules that we use for conditional statements. You just copy over the for every part of the statement unchanged and modify the conditional part just like you do with plain conditional statements. The two predicates are reversed to form the converse, negated to form the inverse, and reversed and negated to form the contrapositive. So I've got a quick example here for us to run through, and this should all be very familiar. We're going to start with the universal conditional statement for every real number x. If x is even, then x squared is even. Right, so they're all going to start. And I'm going to use the logical form here for no other reason than it's quicker to write. For every real number x, it's going to be the same in all three. And what is the conditional part? Well, for the converse, it would be if x squared is even, then x is even. The inverse would be if x is not even, then x squared is not even. And then finally, if x squared is not even, then x is not even. Right? Really nothing new here, right? We're applying the exact same set of rules that we learned about earlier when we're talking about propositional logic. When we talked about conditional statements, we saw that a conditional statement is equivalent to its contrapositive. So that's an obvious question to ask here as well. Is a universal conditional statement equivalent to its contrapositive? To see what's happening with that, right? Remember that conditional statements and their contrapositives are equivalent. So if we pick an individual x out of the domain and it makes the conditional statement true, then it must also make the contrapositive true. Right? So now we can generalize this. If it works for every individual element in the domain, then it works for the entire domain. Right? So what we can say then is that the universal conditional statement is true for every x in its domain if and only if the contrapositive is true for every x in its domain as well. Right, so this means we can say that the universal conditional and the contrapositive are equivalent to each other. Right, just as with conditional statements, universal conditionals are not equivalent to their corresponding inverses and converses. And you can see this by looking at specific examples of conditional statements and then finding a counterexample, that is finding values in the domain for which one statement is true and the other isn't. We'll look more at that in the practice exercises. Now, just like we had converse, inverse, and contrapositive equivalents for our new universal conditional statements, we also have equivalents of necessary and sufficient. And again, there's nothing really particularly new here. They follow the exact same pattern that we've seen before. They all just kind of maintain that for all x part that makes this a quantified statement. And then you do the same thing with a conditional that we did previously when we were talking about propositional logic, right? So just looking at these real quick, a sufficient condition is for all x, p of x implies q of x. A necessary condition, again, does like we've seen before, right? The for all x stays the same. We get the inverse here, right? Not p of x implies not q of x. And finally, right, only if is not q of x implies not p of x, right? Same things we've seen before. So this wraps up our study of predicates and their variations. Right? In the next section, we're going to look at how we can construct and validate arguments with predicates, similar to the ones we made earlier with propositional statements.